The next section, 10.2, is on infinite series. So let's take a look at that. Infinite series. Suppose A sub n is a sequence. Okay, as the ones we just went over. Then the sum, was sigma notation for sum, as n goes from 1 and then you approach infinity, of A sub n is equal to adding all those up. It's the sum of those. So it's A1 plus A2 plus A3, etc. We can put an intermediate, something in between, intermediary, A sub n plus, but we're looking at not finite cases. We're looking at infinite cases. So like that. So that's what we mean by infinite sums. So we're interested in whether those sums converge or diverge. And we'll be going through a number of tests to see what converges or diverges. So it's an important concept in the study of mathematics, kind of some of the foundation and roots of all this stuff that we look at. So next definition is called a partial sum. So partial sums, sometimes referred to as the kth partial sum. So the kth partial sum looks like this. So, the kth partial sum S sub k, so we use S, of the sequence A sub n is this form. You say S sub k is equal to, basically, it's adding up k terms of the sum, is all that means. A1 plus A2, etc., all the way to A sub k. So that's what we mean by so it added up to k terms of the sequence. So then we can look at the sequence of partial sums. The sequence of partial sums of the sum A sub n, the series A sub n, is this. It would be S1, S2, S3, etc., S sub n, and then you keep on going. So you're seeing what that looks like. So that in itself is a sequence. So what we have is S1 is just A1. S2 would be A1 plus A2. S3 would be A1 plus A2 plus A3, etc. And you would keep going like that. Let's do one more. S sub 4 would be A1 plus A2 plus A3 plus A4. So that in itself becomes a sum. Well, then we have a definition that uses the concept of partial sums. So next definition is looking at those sums. So you can imagine what's happening to those sums. If you can figure out what that sequence is doing, then you can use concepts of sequences to determine convergence or divergence. But this is what we rely on. So a series A sub n converges if and only if the sequence of partial sums converges. Only if and only if the sequence of, hold on a second, the sequence, of partial sums, so it would look like this, S sub n converges. Okay, so that is, i.e., the limit of S sub n as n approaches infinity equals L, which is in the reals. And then similarly diverges. So similarly diverges if that sequence diverges. So that's what we use kind of as our foundation to look at all this stuff. So we're going to look at a few kind of foundational examples to see what's going on, then we'll start building tests. So this is kind of in that definition of derivative stage type of thing, trying to explain things, and then we'll get into the actual test of everything. So kind of bear with me on this one as we go. But I want to try to do these where I'm not just doing examples, which is what you will get pretty much online most of the time, not the theory from what I've looked at myself. So let's look at an example where we look at this partial sum and kind of see what's happening. All right, so suppose we have this series. All right, so given the series, so it looks like the series 1 over n times n plus 1. And we'll write that out of the first few terms of that series. So that'll be equal to 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. And you can see that pattern, plus dot, dot, dot. And the nth term is exactly what we have, of course, here. That is the nth term, so it's explicit, so you just write them down. It's easy to do that part of it. Okay, etc. dot, dot, dot. So we're going to do a couple steps here that we won't always do, but this is kind of that warm-up stage of stuff. So A, we want to find S1, S2, S3, and S4. The book actually has this, the one I'm looking at has us do more, but oh, that's good enough. And then B, find S sub n. Now, we won't always do that. We won't always have to find S sub n. This is more just, like I said, trying to show you kind of what's happening. But I want to show it to you this time. The concept of a partial sum is generally more difficult to grasp. So you just study it, read the book a bit, and kind of, dive into it. Don't just take this example as your only thing. Then C, show that the series converges and find its sum. So show that the series converges and find its sum. And again, little disclaimer, finding the actual sum is only done for a few special cases. Most of the time, we're really only looking at whether a series converges or diverges. So the actual sum is more rare, you can call it that, to see what the actual sum adds up to, if it converges, that is. Because remember, these are infinite sums, is what we're interested in. So here's our solution. So A, let's just do some calculations. So just to be clear on what you're doing, you're adding up the terms. So S1 is just 1 over 1 times 2, which is a half. And let's go across. S2 is going to be 1 over 1 times 2 plus 1 over 2 times 3. And I'll save you the arithmetic there. That's 2/3 when you add that up. S3 is 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. And when you add that up, I'll save you the pain of the arithmetic. That ends up being 3/4. And let's do another one, S sub 4. And because I can, I'm going to move that down a little bit. S4 is, so you want it, so part of doing these and understanding them is writing stuff out. You got to get tedious with this stuff. Simplify it, write it out, and study it. Plus 1 over 3 times 4. Oh, and then of course just reading this stuff or listening is you're not going to learn anything. You got to write stuff out and do it yourself. It's the only way you're going to learn this stuff. So S sub 4, this is just get you started. Okay, if you add that up, you get 4/5. And we can keep going. I'll just show you the other ones because I have them. So S5, same sort of process. You get 5/6. S6, add all that up, you get 6/7. Okay, and so that's the sum of the sequence as you start adding them up. So for B, and B is not always, this isn't always something we'll ask. This is just kind of for this case I want to show you. So we can write AN in a different way. We can break that up. So we can write this as 1 over n times n plus 1. And if you break that down, what does that look like? We just did that in one of our integral examples. One of you may have said, or many of you all are thinking, yes, that you can break down using your partial fraction decomposition. So you can use partial fraction decomposition. You end up getting 1 over n minus 1 over n plus 1. So we can write out the partial sums in a different way. So S sub n, we can write that as A1 plus A2 plus A3 plus etc. all the way to A sub n, which will equal, and let me move this over, give myself enough room, that'll equal 1 minus a half plus a half minus a third, and plus 1/3 minus 1/4. And you got to check this stuff as I'm doing it, because I'm not doing it in my head either. I'm copying, but you can show it if you just take your time a little bit. Pause the video once in a while. And then you get 1 over n plus, or minus minus, let me fix that. Minus 1 over n plus 1. So all of that will simplify and reduce down. So if you regroup, we see all the numbers except the first and last annihilate each other and simplify. So 1/2 positive 1, or negative 1/2 positive 1/2. So all of these are gone. So you end up just getting the first one and the last one. And so you end up having that S sub n is equal to 1 minus 1 over n plus 1, which is equal to, and you add that up, and that is n over n plus 1. So that's your actual sequence of your nth partial sum, which is, again, as I mentioned, don't want to be redundant, but I want to reiterate that that's not always easy to find. Okay, so we're doing this as an example, but we can, at that point, once we do find it, if you can, then you can just take the limit of that. So the limit of S sub n as n approaches infinity equals what? And that we've used, you can use all your limit techniques to do that. So when you take the limit of this thing, you can do 1 over n and 1 over n. So this goes to 0, those goes to 1. Right, so, or you just look at the coefficients, however you want to do that one. But you don't have to, argue it. So that limit is equal to, and let me write it out. So it's n over n plus 1 as n approaches infinity. That's going to equal to 1. So the limit of nth partial sums equals 1. So therefore, the series converges and has sum 1. So therefore, the series, it was defined originally, 1 over n times n plus 1 converges and has sum of 1. And when you leave stuff off like this, it isn't being too short or too not rigorous enough. They often do that in kind of higher level books. It's assumed that we're talking about infinite limits. Technically, yes, you'd want to put in your limits. You want to say n goes from 1 to infinity, like that. But if you leave it off, it's assumed it's an infinite limit. That's kind of all you really do. Because finite limits are basically not that interesting for a mathematician, at least. Okay, so let's look at, and then that concept is what's called a telescoping series. So see how everything collapsed in the middle here? When stuff like that all collapses down, it's like a telescope, like the old telescopes that collapse down. So that's called, when that happens, it's called a telescoping series. Telescoping series. And it is somewhat of a special case for sure. Let's look at another example of this. This one is a little different. These are all kind of just those special cases that come up we want to start with first. So next example, given the series, so the series, we'll come back over here so we write it out, is the sum as n goes from 1 to infinity. And I'll use that term loosely, right, when I say to infinity. Negative 1 raised to the n minus 1, and that's it. So your series looks like this. Looks like 1 plus -1 plus 1 plus -1. And you keep going in that manner. And then your nth term is -1 to the n minus 1 plus etc. So A, same type of questions. Find S1, S2, S3, kind of whatever we can manage. See what happens. So you can in the books that I'm using, it goes up to S6, but we won't do those all of those. Well, maybe I'll show them all to you. B, we're going to find S sub n. And then C, well, do you think it converges or diverges, this type of series? We're going to show that the series diverges. Here's our solution. So A, just if you're adding up terms, S1 is just 1. But S2, you're adding 1 and -1. You're adding those first two terms. So basically it's 1 plus -1, which is equal to 0. But then if you add up 3 terms of the sequence, what do you get? Right, you get 1. And then S4, you get 0. S5, you get 1. S6, you get 0. So what's happening is the question. And then B, this is more of an analyzing it. So you're not, you got to say, well, what's really happening for S sub n? So S sub n, again, you're adding up, in terms of the sequence. You're stopping at terms of the sequence. So S sub n is equal to 1 if n is what? Is odd, or 0 if n is even. So yes, that's what you get. So it never converges to a specific value. It never gets close to a value. Remember that the limiting value has to get close and closer and closer. So since the sequence of partial sums which is S sub n, oscillates between 1 and 0, it means that the limit of S sub n as n approaches infinity does not exist. It's a D&E, right? It oscillates. It's like sine or something. It just goes 1 to -1 up and down. It doesn't take on those values in between, but that's what's happening. So hence, the series diverges. Okay. So now let's look at another special case. This one is a special case, but it's one that we use a lot. It's what pivots around everything, well, not everything, it pivots around what a lot of things we do for the future. So this is our next example. Prove that the series, prove that the series 1 over n diverges. So that series is 1, you start at 1, of course, 1 plus 1/2 plus 1/3 plus 1/4, etc., all the way to the nth term is 1 over n plus, etc. So if you start adding up terms of that sequence, what basically happens? So this one you have to show and argue it in a special way. You won't be asked to argue it like this. But we want to group terms together. So if we add this up, so 1 plus 1/2 plus 1/3 plus 1/4. So I'm going to write out a bunch of these terms. So bear with me here. And I might kind of skip ahead because this takes a bit of time. But at least you will see what the argument is or how they might do it. So see how cumbersome this is? So you group these terms like this, and all the way up to 8, and then 1/9 to 1/16, 1/17 to 1/32, etc. And then we look at these different inequalities. So we can see that if we take 1/3 plus 1/4, that has to be greater than 1/4 plus 1/4, which is equal to 1/2. And then if we look at 1/5 plus 1/6 plus 1/7 plus 1/8, and then now, because those denominators are smaller, so if these denominators are smaller, then this has to be greater than, if I just put 1/8 to all of those instead. So if it's 1/8 plus 1/8, etc., and you do that 4 times, plus 1/8, that equals 1/2 as well. And you can do it again. We'll do it one more time here. So if you write 1/17 plus 1/18 plus, etc., all the way to 1/32, and now you write 1/32 each time, and you do that 8 times, then you get 1/2 again. Well, I guess it's 16 times, but okay, you get the idea. That equals 1/2. Okay, so you have that. So then each of these sums has to be so when you look at this concept, you have that S, let's see, you have S sub 4 is greater than 1 plus 1/2 plus 1/2, which is greater than 3 times 1/2. S sub 8. So what we're analyzing basically is what the terms of the sequence are doing. So we can come up with S sub k. So S sub 8 is greater than 1 plus 1/2 plus 1/2. So I'm rewriting the right-hand side of the stuff above, which is 4 times 1/2, greater than 4 times 1/2. 1, 2, 3. Okay, and then S sub 16 similarly, you have 1 plus a half that many times up to a half, which is greater than 5 times a half. So what you can get then is that s sub 2 to the k, right, 4, 8, and 16 is 2 to the k, is greater than k plus 1 times a half. And that's true for every positive integer k. So this, you could keep going, basically, is what the point is here. So this diverges, obviously, right? So as you keep increasing k, then this is going to keep increasing indefinitely, which is actually less than what the sum is for s sub k to the 2 to the k. Now you're stepping in those numbers so that you can basically, show what's going on. So s sub n has to diverge because that in itself is always greater than that. So you can show that by mathematical induction. So you'd have to prove that. So by mathematical induction, this can be shown as true. So this can be proved. The statement above can be proved. So it follows that S sub n can be made as large as desired by taking n sufficiently large, right? So the limit of S sub n as n approaches infinity has to equal infinity, because this guy is going to start increasing, right? That's going to, no matter how large you want, this will always go to infinity. Therefore, the S sub k or S sub n has to approach infinity. Right, so that's important, and again, you won't have to really show that. There's these type of arguments are kind of hard to follow, but what's really important is you need to know for at least a few months that this summation diverges. That is actually called something. So that's what's called the harmonic series. So the definition, so the harmonic series is that. So harmonic series diverges. So 1 plus a half plus etc., which is the 1 over n, right? And you can write that as the sum, and that diverges. So what we'll look at are series that are similar to that, and we're gonna look at. I'm gonna erase this later, but we'll have 1 over n to the p, and depending on what p is, we can show when the series converges or diverges. We may not know what it converges to, but we can say it converges or diverges. And so what I'd like to think of it as is it's going to pivot around